As an example of routing protocol that is based on routing metric other than shortest path, minimum interference routing emerges as a strong candidate. It is especially important because the internet service providers, which make money on the traffic flows for their respective customers and destinations, are very sensitive about the interference which is coming from their competing rivals. In this module, we shall understand what is the phenomenon of route interference. We look at the concept of max flow. Then we'll formulate the minimum interference problem, which forms the basis for routing. The reference is by Anurag Kumar, Majumdar, and Joy Kuri. Communication Networking and Analytical Approach. First, we look at what do we mean by interference on a route. Assume that there is any chosen route, say from a router A, which is a stub router, to another router B, which is again a stub router. This chosen route that carries the traffic between these two networks actually reduces the capacity which is available for demands between other user pairs. Of course, this makes sense because in real world, the traffic is flowing between different source destination pairs by occupying the resources of the backbone network. As I said, this problem is of topmost priority and consideration for competing internet service providers. The concept of max flow is very important to fully understand interference and then to look for reducing the interference based on some routing metric. Max flow between S and T is a scalar quantity measured in bits per second. It indicates the maximum amount of traffic that can be sent from S to T. It exploits or assumes the availability of all possible paths throughout the network. Of course, max flow is only maximum when no other pair is communicating. Max flow puts the upper bound on the total bits per second that can be sent from S to T. With an understanding of interference and max flow, now we look at minimum interference. Minimum interference in an ideal sense implies no interference at all. It means for a sender destination pair, if it has zero interference with another path, it means these two paths are totally disjoint. Minimum interference occurs if the max flow between S and T remains unchanged. Of course, this sounds like utopian or an idealistic scenario. The path used for the A to B demand does not share any link with the path taken by S to T. It means two pairs AB and ST coexist, but they have no links in common. However, we cannot always assume and expect zero interference. We'll rather have non-zero minimum interference such that the paths would not be absolutely disjoint and they would share some minimum number of hops. Now let's formulate the minimum interference routing algorithm problem. We assume that after the A to B flow demands have been fulfilled and route has been established, our job is to maximize the smallest of the max flows for all the pairs arbitrarily represented as S to T is maximized. It actually means, in simple words, that given that a path has already been established for pair A and B, now our job is to look for the path between S and T in such a way that it results in minimum interference with A to B. Let's look at an example now. Let's consider that there are 4 flows inclusive of A to B. So from A to B point of view, 3 flows belonging to 3 different pairs is existing. And if there are 3 paths, for example P1, P2 and P3, and the flows that we are getting are 30, 15 and 6 for the first path, 12, 19 and 8 for the second path, and 3, 12 and 16 for the third path. If we were to maximize the minimum max flow, then we'll have to choose path P2. The choice of P1 and P3 would be inappropriate because then we are seriously compromising on the flow of the third flow in P1 and the first flow in P3. That is why route P2 turns out to be the minimum interference route for the A to B demand.